Okay, welcome everyone to this edition of the BRAG, Brazilian Algebraic Geometry Seminar. So unfortunately, we've had an internet problem and we are not really hybrid, so we are just in person right now, but we are going to record the talk and then make it available for the BRAG friends later. So it is my great pleasure to introduce our speaker in this BRAG, Alessandra Sarti from University of Poitiers in France, and she will tell us about Henriques varieties. Please, Alessandra.
Okay, thank you very much for the invitation. So that's really a great pleasure to be here. So thank you very much to Carolina for this great opportunity. It is the first time for me here, and I enjoyed the week very much. So the title of my talk, as Carolina said, is about Henriques varieties. And so in the talk, I will present several result definitions that are result of several papers we write during different years. So I would say it's a joint work with Samuel Boissier. Works, we'll say. Chiara Kamere and Mark Kniper Wieskirch. It is something that we started to study many years ago in the smooth case, essentially. And now we are coming to the singular case, but also definition changed during the years. And again, as the title says, Henriques varieties are a way to generalize higher dimension Henriques surfaces and log Henriques surfaces. So we'll see that during the talk, all the definition. But maybe just to give a motivation for the definition I'm going to say, let me recall the definition of an Henriques surface. I say motivation introduction. So definition, a compact complex surface is an Henriques surface if we have the two properties, though the canonical divisor of E is not trivial, but it is torsion. 2 times canonical divisor is trivial. And the other property is that the irregularity, which is the 0 omega 1 of E, so the 1 form, which is also the H1 of E, is 0. So this is, as usual, I will call the irregularity of the surface. So the Henriques surfaces are very classical and beautiful objects. For when you look in the Kodaira classification, they are together with K3, tori and their quotient have Kodaira dimension 0. And they have some more properties. So this is the definition. But once you have these two properties, you can show the following in fact. So the fundamental group of E is Z modulo 2Z. And the universal cover is K3. And just to recall the definition of K3, well, K3 surfaces are very similar to Henriques surfaces, but they have canonical divisor, which is trivial, and also irregularity, which is 0. And so we have a map from S to 1 to E. So S in particular are simply connected. K3 surfaces are always simply connected. And this quotient is in fact given, so you have Z modulo 2Z acting on that. So let's say iota. E is then the quotient, S modulo iota, and iota is a fixed point field involution And actually, since these properties, the action on the two form is not trivial, so it acts purely non-symplectically, let's say. Acting on the two form. So if I call the two form on S omega S, so the action is minus omega S. So here write H0 omega 2S generated by these two forms. And so this action means non-symplectic. But what is interesting here is this free quotient from AK3 surface. And maybe one remark more is that Enriquez surfaces are all projective. So I don't need to ask it. So everything in my talk will be essentially projective, but here I don't ask it because essentially it was Nick Cooling showing that if a K3 surface has such of non-symplectic automorphism, then it is always projective. You can construct an M-pole class, an embedding, and so you get an M-pole class on E. Let's give an example of Enriquez surfaces. I will call this example 0, because I will come back later. So example of Enriquez surface. Well, let us start with a K3 in P5. Well, first maybe consider the following involution. So the aim is to construct to consider a K3 in P5. But let me start by the following involution of C6 to C6. That does the following. So I send x1, x2, x3, y1, y2, and y3 to minus x1, minus x2, minus x3, y1, y2, y3. And in fact, it does not play any role if I change the coordinate on the sign on the x, on the y, nothing changes. We will see in the construction. Then, of course, its involution induces an involution on P5. And we want to consider invariant quadrics. So, and an invariant quadric in P5 has the equation as follows. Well, just to split the variable in two parts, well, I have a quadratic form in the x, quadratic form in the y, and that's all. So I have q1, x1, x2, x3, plus q2, y1, y2, y3, equal to 0. So both have degree 2, homogeneous of degree 2. Okay. And I can take 3 of them. So I consider all this quadric, and inside I can choose 3 of them generic. So j equal to 1, 2, and 3. And of course, so the involution preserves these quadrics. So iota preserves Qj. And if you intersect the 3 quadrics, the fixed locus of iota is empty. This is quite easy to see because you end up at the end an intersection of 3 conics in the plane, and 3 conics in the plane does not meet in general. But then this is a K3 surface. It's a complete intersection in P5 is K3. Let's call it X2. And so we have found a K3 surface with a fixed point free involution. And so the quotient is then in an Enriquez. So let me call again iota the automorphism of the K3 is equal to E is an Enriques surface. So this is a nice example. And it's really important to see that we have the same number of x and y, and we change the sign for the x or the y, and we get this example. So this is quite interesting, but we want now to generalize this in higher dimension. So I'm of my talk generalize all of this in higher dimension. So actually, in my talk, I have time. I will have two parts. I will say first in the smooth setting, and then I will go to the singular setting and say something closer to Enriques surfaces, which are called log Enriques, that admit some mild singularities. Okay, I will then go to, after this motivation, to the notion of Enriques manifold. So I say first the smooth setting, and I give you first brutally the definition, and then I will give you several examples and discuss this definition. So Enriques manifold. So here comes the definition. Well, this definition comes from several people, actually. Auguste Schroer in 2011, Boissier, Nipper-Wieskirchen, and myself, always 2011. And we give a new version of the definition recently with Kammerer in 2024. And I will explain because we will see. So the definition, original definition here, so these are two different definitions of the same, not exactly the same object, but each has a motivation for that. And we conclude, so we think that now there is some reason to have a new definition. But in any case, the X are compact, let's say a projective complex manifold. So I ask for projective. Is called an Enriques manifold. If it satisfies two conditions that are very, very close with what we did in dimension 2, there is an integer d, d different from 1, such that d times the canonical divisor is trivial, but d prime kx is not 0 for any 1 smaller than equal than d prime smaller than d. Okay, like for Enriques, we're asking two torsions. Then I will come back maybe about the two torsion fact. But here we say, okay, I don't want trivial canonical divisor, but I want that some multiple of that is torsion. So some multiple of that is trivial. And the second condition is exactly as in the case of Enriques surfaces. I ask that the irregularity is 0. Second condition. This is always called, I write it every time, it's called Qx often, is equal to 0. So in dimension 2, if you want, this is exactly actually the definition of Enriques. Why? So remark. If dimension of x is 2, then x is Enriques surface. This is because if you remember the classification of surfaces, well, if you start already with the K3, the only possibility to have a free quotient are involution. That is, for example, Lefschetz formula can tell you. Of course, you can do also free quotient of 1 billion surfaces, but then this condition is not satisfied. So you get what is called B-elliptic surfaces and other kind of surfaces. So this is very similar to Enriquez surfaces. And to convince you, I want to give a generalization of example 0. So we'll discuss several examples and several properties. So for example, we have seen that for Enriquez surfaces, the universal cover is a K3 surface. Then we can see what happened here. So we'll see, for example, appearing EHS manifold and Calabi-Yau manifold, and so on. But let's see this example. Well, I want to do more or less the same that I did here. So I have to put the right number. So again, I call it J. And now I go from C to N plus 2. To C to N plus 2. And let me write it that way. So I have x1, xn plus 1, y1, yn plus 1. So I will call this x and this y, so that let me just write in the compact form minus x, y. So I change the sign of the x, and I don't change the sign of the y, exactly as before. And of course, this induces an evolution, iota, on P to N plus 1. And now I want to do the same thing. I consider invariant quadric for this action, which are done exactly in the same way. So invariant quadrics. Again, are of the form Qx, 1 plus Q2y equal to 0. So both have, again, degree 2. And I take now N plus 1 of them. So this is in P to N plus 1. And I take J from 1 to N plus 1. And now I take the complete intersection of that. So again, Calabi-Yau, this manifold that is Calabi-Yau, I will give a definition in a second, so can be constructed in a very similar way as K3. So this manifold is complete intersection, is a Calabi-Yau manifold. Of dimension n. That's why I call n. And of course, if n is equal to 2, well, it's exactly what we have had before. What is for me a Calabi-Yau manifold? Because there are several definitions of Calabi-Yau manifold. So for me, Calabi-Yau means the following. Well, trivial canonical divisor. And the Hodge number H0 omega j xn is 0 for any j between 0 and the dimension of xn. So there are several definitions of Calabi-Yau. Sometimes Calabi-Yau is just meant when 0 first Chern class. Sometimes there is a stronger version of that, asking that all étale covering satisfy these conditions. But for me, let's say, is that the definition of Calabi-Yau. So this Calabi-Yau manifold and has an evolution, which is, again, one can compute, fixed point free. One just play a bit with the equations. And so we get a free quotient. But now one should be a bit careful here because something happened. So we get a free quotient xn modulo iota. And of course, the question, is this an Enriquez manifold? One would feel like to say yes, but it depends. In fact, we will see in a second on if the definition is even or odd. So let me write down the Lefschetz holomorphic formula on xn. So the answer is, well, I'll give you a second answer. So to answer the question, consider Lefschetz holomorphic formula. Saying that the Lefschetz number, Li, is equal to the following alternating sum to n. So recall the dimension of xn is equal n minus 1 to the power j, the trace of the action of iota star on h0 omega j bar. And that's all. Conjugate. Okay. But this is Calabi-Yau, so I'm left with the h0, so this is 1, plus actually the action on the highest power. And just to fix the notation, I call the volume form. Let me call this C times Vn. And so my iota star will, so I have a minus 1 to the power n here, let's say plus, times epsilon, where epsilon is just the action of iota on the volume form. And of course, epsilon can be plus 1 or minus 1. But the Lefschetz holomorphic formula tell us something more, because when the fixed locus is empty, this must be empty. So fix iota xn empty tell me that Li is 0. So the converse is not true, but one direction is true. And so, well, I have here to be equal to 0. So we have two cases. So maybe I go to the other side. Depending on n even and n odd. I do not want to, well, let's erase the definition. We have two cases. So 0, so let's say n odd. We have that 0 is equal to 1 minus epsilon, and n even, then 0 is equal to 1 plus epsilon. So in that case, means that epsilon is equal to 1, so that the action of iota on the volume form is identity. In that case, epsilon is equal to minus 1, and so the action of iota on the volume form is minus Vn. Well, the first case then cannot be Enriquez, because then the volume form go to the quotient, and we have a canonical divisor which is trivial. So this gives me the case of xn modulo iota Calabi-Yau. So that's in some sense not too difficult to say, because the cohomology of the quotient is the invariant cohomology upstairs, and so all the intermediate that odd number are 0. But since I have this condition, the canonical divisor is trivial, and so it's not Calabi-Yau, not Enriquez. But in that case, as for K3, I kill the the volume form. And so this is what exactly is Enriquez. So in that case, we have produced example of Enriquez manifold in even dimension. So this example somehow generalizes what happened for K3 surfaces, but here happens something, so that one cannot say I have Enriquez with this example, at least with construction, Enriquez manifold in any dimension, but I have in even dimension. Actually, this will not be strange, because in a second I will show a more general result. And we will see that for Calabi-Yau manifold, I can only have even dimension, and the quotient is by an evolution. But this is a nice example, because it generalizes exactly what happened in dimension 2, so exactly the construction. So I can then give another definition, defining the type of the Enriquez manifold. In fact, so if you think about generalization of K3 in higher dimension, you have EHS manifold and Calabi-Yau. So one can, in fact, split at least Enriquez manifold in two types, quotient of Calabi-Yau, a quotient of EHS manifold. So let me say the definition. Again, this is the result of the same paper of Giesel-Schroer. And so let X an Enriquez manifold. And so dkx is trivial, but d prime kx is not trivial for 0 prime is d, and this is different from 1. So the smallest d is called the index, moreover. So this d is called the index. Just to fix the notation. So Enriquez surfaces, for example, are Enriquez manifold index 2. So then X is called of Calabi-Yau type if, well, each time that you have such a torsion divisor, you can construct an ramified cover, the canonical cover, so it's determined by this divisor. Let's say y to x, so it's d to 1. It is exactly what happened. Remember, for Enriquez surface, I have these two torsion canonical divisor, and then I construct my universal cover, which actually is that one, and this is d to 1. Y is a simply connected Calabi-Yau manifold. And in this case, we will show in a second. As I said before, this is not just a special case with index 2. We have that the index d equal to 2, so x is really a quotient of y by an evolution. So this d is equal to 2. And the dimension of y is even, which is also the dimension of x, of course. Okay. And the second case is for EHS manifold. So the interesting fact here, we can only have two torsion, no more. But the case of EHS manifold will see behave a bit different. So X is called of EHS type. Sorry. So EHS stands for irreducible holomorphic symplectic. Type. I recall in a minute what is EHS. If the canonical cover Y, so we have Y D21 to X is EHS. And if dimension of Y is equal to n, then D, the index, divides n plus 1. Just recall what is EHS, just for a second. Well, EHS, again, is one of the other generalization of K3. So this means that, let's say, given that way, that it is simply connected. Okay, it's simply connected. And there is a unique global holomorphic 2 form, let's say omega y, never degenerate. And this implies, of course, that also ky is trivial and dimension of y is always even. Because this gives an alternating form on the tangent space, and so it's even. So here, that we get even dimension is not so strange because y already have even dimension. So this is the definition, and these are consequences. So always even dimension. So what we remark here that we have a priori many more possibility for the index. So there we said, okay, the index is 2. I will give a very easy proof to show where this condition comes from. And here a priori, well, there is 2 questions. I mean, in that case, I convince you it exists, example, but does exist example, and which index can I have here? Okay, before to do that, maybe I want to give you an idea of the proof. It's an easy proof, why I get this condition and that condition. And then I will discuss example. Well, one thing is that I can write the key of OY thanks to this covering, which is times D times the key of OX, because the covering is unramified. And then let's look what happened in the EHS case and the Calabi-Yau case. Well, in the EHS case, one can compute the key of an EHS manifold. So if YHS, so I start with the second case because it's more easy. Y is EHS. Then the power of these 2 forms generate the cohomology. So the H0 omega J Y. So this means that here happens something only in even dimension, and we have only one generator. So one compute easily the key of OY is equal to n plus 1, where 2n is the dimension of y. And so that's why we find immediately that D must divide n plus 1. So that's a restriction, easy restriction on the index. If y is Calabi-Yau, well, again, write it down the key of OY. But then again, you are left only with 2. And so this is essentially 0 if n is odd, because I have 1 minus 1, and 2 if n is even. Okay, but now I know that this key of OY is d time key of OX, and this d is the torsion of the canonical. So it's different from 1, and of course different from 0. So the first case cannot happen, because the key of OX is 1. So why is 1? Well, essentially, you have the H0, of course, and then what comes here for X is the invariant part above. But then the invariant part above, as I say, so that's 0, and nothing comes from the volume form because it's not trivial. So this is just 1. So in that case, we have that this is equal to, this must be equal to 2. So this is equal to D. And so we must have 2. And that is done, because then we know that D must be equal to 2, and we are exactly in the even case. So okay, the n odd cannot happen, because otherwise I should have key of X equals 0, but it's not the case. This is exactly. So the proof is very easy, but it tells us, okay, with Calabi-Yau, I cannot hope to have a higher index. Because the next question, of course, now I show different properties, is to find example of Enriquez manifold. So the question. Okay, let's say some words. So there are actually even more questions. So one, want to have example of a Enriquez manifold, and then to know which index can we have. So in particular, which index D, so D times K is trivial, are possible. So let me give the list of examples that are known, and we will see that, well, from Calabi-Yau we hope nothing more than index 2, but in fact in EHS we have something more. So known example until now. Well, let me first give maybe with the Calabi-Yau. I give you already an example. So let's say Calabi-Yau type. Our example 1, let's say. So it was xn modulo iota, where xn is a complete intersection of quadrics in P2n plus 1. And here the index is 2. Okay. Another one is, but that is not the only one. There's another example that was constructed, so first is that one, that was constructed by Ogizio and Schruer. So you take an Enriquez surface, and in fact, the first thing one would like to do, so you take a K3, you make the Hilbert scheme, and you get an EHS manifold. And one would like to take, okay, now I take an Enriquez surface, I make the Hilbert scheme, I get an Enriquez manifold, and that's true. Then the Hilbert scheme, En, which is Hilbert n, is an Enriquez manifold Calabi-Yau type. And this was shown by Ogiso-Streuer. I should comment on that, because at that point, so when Ogiso-Streuer gave the first definition, they exclude the case of Calabi-Yau type, so for different reasons. For them, Enriquez manifold is just a free quotient of an EHS manifold. And then when he reconsidered the definition to generalize in the singular setting, we are thinking about Calabi-Yau. And actually, for us, it was natural to include Calabi-Yau because there is this generalization in higher dimension of the example with K3. So it seems to be natural to include them. And also this, actually the definition we gave now, it was different for our original definition with Samuel and Mark Knipper-Wieskirchen, because at that time we include Calabi-Yau, but we had some strange condition on the key of the quotient that it was not left our examples that were in fact interesting. So maybe this is a good definition, let's see. But anyhow, we have these two examples. Of course, the question we are a bit thinking about now, if these are really two different examples, or if, for example, this I think is a bigger family that you can construct, this is a smaller one, 10-dimensional. If one can see, for example, some relation between two families or subfamily that are correlated, so one don't know. So I have these two examples, but are really different, so I don't know. Let me give example of EHS type. Well, the first example, again, is a very natural one, because you take SK3, you take S with a fixed point free involution, one Enriquez involution. And the other thing that one would like to do, that's natural, well, you take now the Hilbert scheme of the K3. This is EHS. That's by work of Boville-Fujiki. Fujiki was n equal to 2, and then Boville did the other. And of course, when you have something like that, you can induce an evolution that I call En by using that iota on Sn. And sorry, the Hilbert scheme. And for n odd, one can show that so the dimension is always even, but there is a difference between, so the dimension here is 2n. But here there is a difference between n odd, and so for n odd, the fixed locus of iota n is empty. And so we have an Enriquez manifold of EHS type. Okay, observe that for the moment, everything again here was index 2. But here again is index 2 because an evolution. If you want, well, one can see that n is odd for directly, but it comes indeed for that because 2 divides n plus 1, n must be odd. So one can see it that way. But in fact, there are examples of not index 2. I will not give it now because the construction is a bit long. So long to explain, so I don't want to say too much about that. But it was something we showed at that time, and the same simultaneously. So it was a paper coming out. So the paper of Ogiso-Streuer and our paper come out simultaneously. So that was the paper. Always 2011. That so it's here. Exists Enriquez manifold. of course, are of EHS type, of index 3 and 4. So we have different index. And to construct them, actually one do a very similar construction as here, but instead of taking the Hilbert scheme of a K3, you start with the Hilbert scheme of a abelian surface, and then you take the Kummer surface associated with that. That's, again, an EHS manifold. And with the Kummer generalized Kummer surfaces, so the construction uses generalized Kummer manifold. So just to remind you what is the definition, you take an abelian surface n plus 1 times. So this is abelian surface. You make the symmetric quotient, so let me call this an plus 1. And you have here an plus 1 modulo sigma n plus 1. You take the Hilbert scheme, let's see, as a resolution of the singularities. But then here you have the summation map to A. And then you take the fiber over 0. So here is a, let's say, writing that way, x1, xn plus 1, go just to the sum. And here inside you have the 0. And so the fiber over the 0 is generalized Kummer manifold. So let's call that psi. And so Kummer n A is 0. And dimension is 2n. Okay. And actually the construction starts with a product of elliptic curve here, special one, with some automorphism. This induces automorphism of the generalized Kummer manifold, and then we can show that if x point free and find this quotient and Enriquez manifold. Since I start with elliptic curve, one could say, okay, but elliptic curve can have all the order 6 multiplication, but it does not work. We have checked, so the same construction will not work, will produce something that has fixed point. But this just to give an idea, so this kind of example are different, and index 3 and 4. And that's all. So until now, we have no more example. So remark. Until now, no more example. Are known of that. So we start to also consider, I don't know, Fano variety of line of cubic 4, but this does not give anything new. And I don't know if one can have more index with the EHS manifold. At the moment, we are working much more about this example with Calabi-Yau manifold, maybe to find more example, or as I say, try to show that maybe we have only one family, I don't know. So it's more a work in progress. This is with Samuel and Anna Palomino. Let's say study example Calabi-Yau type. I'll say 1 plus 2. At least I'm ready to see here if these two families are really different or are the same, and then study more Calabi-Yau complete intersection, for example, if one can get more Enriquez manifold. There is another, I want to say another recent result, because EHS manifold, there are 4 deformation family. You have the Hilbert scheme of a K3 surface. You have the generalized Kummer, but you have also O'Grady 10 and O'Grady T example. And there was a result, recent result by Billy, the 2 Jovenzana. and Grossi, saying that this was exactly, they came out at the beginning of the year, that Enriquez manifold cannot be quotient of OG10 manifold and the deformation. So of course also for OG10, so it's order dimension 10, one can see which are the possible index and then show in their paper that this is not possible. But for the moment I have only for OG10 and not the other EHS manifold. So it would be nice at some point, you see this condition on the index I gave is very easy, so there is nothing special in that. Already maybe find some condition on the index for EHS manifold to say only some index are possible and no more. That's not known. This is what is known on this quotient. Maybe I want to say about the singular setting, but I wanted to give you another motivation because until now I have spoken about two types of Enriquez manifold, which are EHS type and Calabi-Yau type. And one can ask, why consider these two types of Enriquez manifold? There are more. So the question that there are more type, I don't know, but there is a reason why to consider these two, which is the Bouville-Bogomolov decomposition theorem. Why considering Enriquez manifold? But the answer is the Bouville-Bogomolov theorem. Take a X compact complex Kähler manifold is a real function class equal to 0. Then there is a finite étale cover let's write it in that way. Product of Vi, I'll tell you in a minute what it is. Product of Wj, product of T to X, where these are EHS. These are simply connected, one can say, Calabi-Yau, and this is a torus. So somehow these are the, one say always the building block to construct all these manifolds with zero first chain class, and an Enriquez manifold is here. So it seems natural to construct this, to consider EHS and Calabi-Yau type. Torus type is not possible because of this condition of irregularity. So remark, torus type is not possible for an Enriquez manifold. This since this condition. This is because we consider cyclic quotient of tori, and when we have a cyclic quotient of a torus on a abelian surface, like in case of B elliptic, then this irregularity is not 0. This is not true if you don't have a cyclic quotient. But since we have this cyclic quotient, so this is not possible. Just 3 minutes maybe to say a word about the singular setting. That will be very fast, but So at least the motivation for what we do recently. Which is a singular setting. Well, there was a work of Zhang, Ogiso, let's say Ogiso, in the 90s that defined log Enriquez surfaces. And the definition is the following. That was more for Zhang, but then Ogiso gave a lot of did a lot of result too. One take Z, projective normal surface, or over C, with at worst quotient singularity. And no ADE, because in fact the ADE one can remove them and does not change very much. And then Z called log Enriquez. Surface. If, again, so the definition is very similar. The canonical divisor is torsion. And the regularity is 0. Two conditions. But in this case, it shows, in fact, that we can have a higher index. So this torsion is not necessarily 2, but is much more. For example, quotient of K3 by non-symplectic automorphism. So an example that was very much done by that people is a quotient of K3. Let's say some non-symplectic automorphism, I will not be not very be precise, with only isolated fixed point. And here you have plenty of examples. So there are many index, until the index, I think, 19, so there are very many. And so just what is the definition higher dimension, and then I will finish. So in higher dimension, that was done recently, so the generalization in higher dimension was studied by several people. So there was our paper, but also a paper by Denisi, Rios Ortiz, Tsakanikas, and Xie, both at the same time. So it seems that when people get interested in Enriquez, then there are always two papers coming out at the same time. That's a bit, but they consider that more in the framework of a minimal model program. So, and the definition is the following. Again, the definition is not the same in the two cases, but anyhow. So first, what is a K-torsion variety? If it is projective, normal, KLT singularity, that somehow generalizes what happens there. So I will not define KLT singularity, but let's say somehow to generalize singularity that we have simple singularity. With torsion, but not trivial. Canonical divisor. So again, the definition of Enriquez, you can imagine now what it is. Well, it is a K-torsion variety with zero regularity. So definition, X is a log, or let's say an Enriquez variety. Log Enriquez, sorry. If X is K torsion, and the regularity is 0. Okay, now just let me comment on that. Of course, one want to have example, and here the geography is much more rich. You get much more example, because in the same way, for example, you take an EHS with a non-symplectic, some non-symplectic, let's say non-symplectic of prime order, having only, no, any, sorry, in that case work for any, then we have an Enriquez variety. So X example, non-symplectic sum, again they say it that way, non-symplectic quotient of EHS manifold. And as I say, here I get plenty of example. It's very hard to understand automorphism of EHS manifold. It's a very complicated task. But it's more easy if you start using the manifolds that come, for example, from the K3 surface, or from the abelian surfaces for generalized Kummer. And then you have many index, for example, that are possible. So here, yes, there are many examples with Fano varieties of line and so on. That's why maybe go to the smooth setting, to the singular setting, make these things even more interesting, because you have many possibilities. And also in this case, you can define something very close to EHS type, which is more ESV type, or PSV type, different type, and Calabi-Yau type. So, and then start to study all the different possibilities. But I think my time is over, so that, yes, I will stop here.